today, and then Monday you guys have a Math Excel work day. Monday night is when 7-6 is going to be due. Tuesday is when 7-7 is going to be due. Those are your last two Math Excels. And then Tuesday next week is going to be your last quiz over 7-6, the polar stuff, and then this 7-7. Okay, so that's what's coming up. All right, so last bit of chapter 7 is polar form of complex numbers and de Moivre's theorem, which we'll talk about at the end. Okay, so complex numbers are our imaginary numbers. And standard form of a complex number, you guys know, it's a plus bi. Okay, we call a the real part, we call b the imaginary part. You guys have seen those forever, right? So what we're going to do in this section is we're going to start thinking of these as things we can graph. Okay, so in order to graph a polar number, we have to change our axes a little bit because there's not an imaginary axis on an xy axis. So when you graph a polar point, you have a real axis. That's where the A is going to go. That's our x-axis. And you have an imaginary axis. That's how high or low you're going to go based on whatever your B is, what's in front of your eye. And that's where the point will be plotted. So if I was going to plot the point A plus BI, or a value to represent that complex number, I would go A to the right and I would go B up on this real imaginary axis. All right, so we're just going to practice a couple of those at the bottom here to start. So you can just make on your paper like a brief little, tiny little grid, okay, and label it real axis, left and right, imaginary axis, up and down. You've got a couple points plotted on there for you already. If it's just a real number, it's only going to be on the real axis. So like the number -3 would be on the x-axis 3 units to the left. Or if it's just an I term, it's just going to be an imaginary number, so it's on the y-axis. So like -2i would just be 2 units down. Okay. So then let's say I wanted to plot 2 plus 3i. We'll call that point A. All right, so 2 plus 3i, I would go 2 to the right and 3 up. There's point A. Point B, -3 plus 2i. So I would go 3 to the left and 2 up. There's B. 4. So you can think of it as 4 plus 0i if you want to see both pieces of it, but it's just 4 units to the right. And we'll call that guy point C. Point D, -2 minus 3i. So I would go 2 to the left and I would go 3 down. So you can see based on the signs, like 1 positive, 1 negative, or 2 negatives, or 2 positives, it's matching up with the quadrants we know already because of the direction we go to graph things. And then 3 minus 2i, the first term's positive, second term's negative, so I know that's going to be in quadrant 4. That's going to be point E. 3 minus 2i would be right there. Okay, make sense how we graph those? Any questions? Perfect. Okay, so now that we can graph it, we can visualize the next thing we need to be able to calculate. So the next thing we want to be able to calculate is the absolute value of a complex number. This is also called a magnitude, and you'll see why it's called a magnitude in a minute, or a modulus. We don't use that word as much, but you might be asked to find the magnitude of a complex number. It just means absolute value. So a lot of times we think about absolute value as being like something that just makes everything positive, because that's how it works with real numbers. But absolute value means distance to 0 is its true definition. Okay, so if I say the absolute value of -3, we know the answer is 3 because it's 3 units to 0, but we just know, okay, it's positive, whatever that is. In a complex numbers, when we graph them, are oftentimes located like in one of our quadrants. So if I want to find the absolute value or distance to 0, we create this familiar little picture that we have, right? A is our left, right. B is our up, down. We get this cute little right triangle, and the absolute value is the distance to 0, and it ends up being our Pythagorean theorem, the square root of the legs squared and added together, right? So a squared plus b squared. Okay, so now this is the third time we're seeing this formula pop up. Okay, so we saw it with our vectors, calculating the magnitude. It was an x and a y there. We saw it with our polar coordinates, calculating r, right? We did x squared plus y squared to get r, and now you're seeing it again with complex numbers. You want the absolute value or the magnitude, just a and b, instead of an x and a y, okay? All right, so let's practice. Find the absolute value of the following complex numbers. -5 plus 12i. All right, so it's just the first component squared plus the second component squared. Think of I again, just kind of like a label. It tells me it's my vertical component, so we don't need to worry about plugging I into a formula or anything. Okay, and that would be 25 and 144, which would be square root of 169, which is 13. Okay, so the absolute value of that complex number, or the distance to 0, is 13. And it's always going to be positive because it's a distance that we're calculating. All right, we know the absolute value of -7 is 7. You can use this formula too, though. This works for all kinds. I can do -7 squared plus 0 squared. 0 is the imaginary component on that number if I write -7 plus 0i, right? So -7 squared would be 49. Plus 0 squared is still 49. And you can see we get 7. Okay. Can you tell me what the absolute value of I would be? Imagine if you had to graph it, where it would be, and how far that would be to 0. If you graphed I, what would you do? You start at the origin and go 1 unit up. So the absolute value of I is 1. You could also think of it as 0 plus 1i. You could do 0 squared plus 1 squared, which is the square root of 1, which is 1. Okay, but just again, distance to 0 is what we're getting for each of these. Any questions there? Absolute value of a complex number. Yes?
How do you decide if it's negative or positive?
It's always positive because we are calculating a distance for this, so we don't have to worry about plus or minus. All right. Next. All right, we've got 4 formulas. These will look familiar to you. The only difference between these formulas and what we saw in the last section, where now instead of an x and a y for a horizontal and vertical component, we have an a and a b for a horizontal and vertical component. Everything else is the same. Okay, so we know that a goes with cosine, or x goes with cosine. B goes with sine, like our y goes with sine. And then we know to find r we can think of as that absolute value to square root of a squared plus b squared. And then if we want to find theta, we use tangent to find that. We do b over a. Okay. Sometimes, by the way, the angle theta is called the argument. Okay, so if you are asked to calculate the argument of a complex number, it's just asking for that angle. And then another formula that's going to look new, but it's not really, is polar form of a complex number. And that's that guy up there that I circled in green. This formula, polar form of a complex number, is actually the formula that we saw with vectors. You remember with vectors, we had the magnitude out front, and then inside we had cosine theta plus sine theta, right? Same format here, okay? So now we're going to take the magnitude, or the absolute value, the cosine of an angle, sine of an angle, but instead of with vectors, we had I and j. Here with complex numbers, we have a real part, so no I, and then we have a complex part, imaginary part, the I. So the next thing we're going to do is we're going to practice taking a complex number and putting it in polar form. You're going to see the calculations we're going to do are going to look really familiar, okay? It's very similar to what we've been doing, just another like context we're applying these same formulas to. Okay. All right, so our first one is -1 minus I. I want to put it in polar form, which pretty much means I need to find r and I need to find theta. As soon as I find those, I'm good. Okay, so to find r, I'm going to first actually label my a here is -1 and my b here is -1. Those are the numbers in front, my real part, my imaginary part. All right, so I need r. R is the square root of the first component squared plus the second component squared. So what am I going to get for r? Rad 2. Looks really similar to what we did with polar coordinates in the last section, right? Then to find theta, tangent theta equals b over a, or in this case, -1 over -1. So tangent equals 1. Now we know there's going to be 2 answers to this. So just like with polar coordinates, we're going to look at our quadrant. If you graphed 1 minus I, what quadrant would you be in? You would be in quadrant 3 with that real and imaginary axes. So our theta needs to be an angle in quadrant 3. It doesn't say here degrees or radians. Sometimes it'll say write your argument in degrees or write your argument in radians. Let's just do degrees for now. Where does tangent equal 1 in quadrant 3 in degrees? $225. That's what we're looking for. Okay, so now your answer, you're just going to fill in this formula. I sine theta. There we go. R is rad 2. Cosine 225 plus I sine 225. And then you stop. That is your answer in polar form. Now, could I simplify this? Yes. And if you simplify it, we'll do that actually on the next page, you actually just get right back where you started. If you simplify it, you'll get -1 minus I. So that's how you can check your answer. But we want it in this form for some other calculations, and you'll see what those are in a minute. Okay? You guys try the second one. I'll give you a couple minutes. Find R, find theta, put the complex number in polar form. Let's check answers. I got 2 and 60 degrees. That? Yeah. Okay. Any questions? Putting a complex number in polar form. Okay. So I'll show you on the next slide then how we can go the other direction. If you have, or you can check these too. If you have a complex number in polar form, these ones are written with radians. It could be degrees though too. And you want to put back in rectangular form, that's just standard form with the a plus bi. That's all it's asking for. So all you do is simplify. That's it. Okay, so can you tell me what the cosine of pi over 6 is? Rad 3 over 2. Plus I, what's the sine of pi over 6? Times a half. And then what's going to happen when I distribute my 2 in? Denominator is going to cancel. So I'm going to be left with rad 3 plus 1i, or just rad 3 plus I. We'll just do one of those because they pretty much work the same way. Okay, so those previous problems, that's how you can check it. You can just simplify, distribute through, you just get right back where you started. Good? Okay, next thing I need you to write down. We've got 2 formulas. These 2 formulas, once we have a complex number in polar form, we can multiply the 2 complex numbers, or we can divide the 2 complex numbers. These look a whole lot complicated than what they actually are, and you'll see in a minute. To multiply 2 complex numbers in polar form, you multiply the r's, and you add the angles. Other than that, if you look at like the format of what we have there, there's going to be a number out front of a parentheses, and then cosine of an angle plus I sine of an angle. So it's the same format we just saw for polar form, but to get the r and get the theta, you have instructions. To multiply the r's, and you have to add the angles. If you want to divide 2 complex numbers in polar form, you divide the r's and you subtract the angles. Okay. You guys have in the past multiplied and divided complex numbers, like back in, I don't know if you did it in Algebra 1 or Algebra 2, but like you did problems like 3 plus 4i times -2 minus I. That's multiplying 2 complex numbers. That's what we're doing here. They're just in a different form. Or dividing 2 complex numbers. The dividing actually was the one that was a little messy because I is by definition the square root of -1, and you can't have a square root in the denominator, so you had to use conjugates with that one. So this can simplify the process a little bit if you put it in polar form and do the division that way. So I'll give you a second to write those formulas down. Okay, got it? All right, let's do an example. So we have two complex numbers, and that little thing wants to go away. Hold on a second. There it goes. Okay, so Z1 is a complex number that's already been put in polar form for us. So 5 times the cosine of 75 plus I sine 75. So they figured out the r and theta already for us. And Z2 is 2 cosine 60 plus I sine 60. So we're going to use those formulas you just wrote down to multiply these and divide these. And then we're going to leave answers in polar form. Make sure when you're doing Math Excel, you read the instructions really carefully. If it says leave answers in polar form, that's usually a good thing because you don't have to simplify all the way. You can just leave it once you find your angle and your r. If it says put answers in rectangular form, you got to go a little further and simplify all the way. Okay. All right. So if I want to find Z1 times Z2, the first thing I have to do is multiply the respective magnitudes, multiply the r values, which are just 5 times 2 here. Then cosine, and to get this angle, we're going to add the two angles we have together. So it'll be well, I'll do them in order. 75 plus 60 plus I sine, that same thing, 75 plus 60. So the answer in polar form is going to be 10 cosine 135 plus I sine 135, and that's it. The only thing that would make this a little more difficult is if it said rectangular form, you just keep simplifying. Use your unit circle. If it's Z1 divided by Z2, it's going to be similar, except we divide the r's and subtract the angles. If I divide my r's, it's just 5/2, or you can say 2.5, that's fine. And then you can probably just do this all in one step. If I do 75 minus 60, I get 15. If you get a negative angle, you just want to simplify it with your even-odd identities. Cosine, you can drop the negative sign, bring it out front, but that's it. Okay, so not a difficult formula. It looks a lot worse than it actually is. All right, we're going to use the multiplication formula to figure out the next thing we need. Okay, so let's say we have Z. Okay, this complex number, it's in polar form. R is whatever its magnitude is, theta is whatever its argument angle is. I want to find Z squared. So squaring something means to do what? What does it mean to square something? Multiply it by itself. So we're just doing Z times Z. So if I use my multiplication formula to do Z times Z, I would multiply their R's. So what's R times R? R squared. And then to get my angle, I would add the angles together. So it would just be theta plus theta. What's theta plus theta? 2 theta. Plus I sine 2 theta. All right, that's what Z squared is equal to. What could I multiply to get Z to the third? What two things could I multiply to get Z to the third? Z to the second and Z to the first, which we have both of those. Multiply their R's. Well, one of them has an R squared and one of them has an R. So if I multiply R squared and R, I get R to the third. And then cosine, I'm going to add their angles together. 2 theta and theta. If I add 2 theta and theta, I get 3 theta. Okay, are we sensing a pattern yet? So if I said, tell me what Z to the nth power is, what would you write? Go ahead. That is de Moivre's theorem. Write it down. Okay. This allows us to take any complex number to any integer power. Okay, so positive or negative power. This, I think, is the #1 reason I would ever want to put a complex number in polar form. If I gave you a problem and said, take, oh, I don't know, -7 plus 4i to the 87th power. Okay, that means there's no shortcut. You got to FOIL that out 87 times. That is going to take you forever, and you're probably going to make a mistake, and it's probably going to be wrong, right? But if we can take that complex number and put it in polar form, all we have to use is this, and we have that answer to that very high or very small power if it's a negative exponent. Okay, so this is saving us a ton of time if we're able to do this. So let's do an example. At the bottom here, okay? We have the complex number, -1 plus I. We're going to use de Moivre's theorem to take it to the 8th power and to the -12th power. Okay, so the first problem is we're taking -1 plus I to the 8th power. Okay, by hand, you're FOILing that out 8 times. With de Moivre's theorem, he says, okay, find R and theta first. Put it in polar form. So R, we know how to do that, right? That's the square root of -1 squared plus 1 squared. So that gives me square root 2. And to find theta, we use tangent. Tangent of theta is your b divided by your a, or your x divided by your y, however you want to think about it. The second component here is 1, and the first component is -1. If I divide them, I get -1. So we're trying to figure out, where do I have a tangent of -1? Remember, you can think about what quadrant you're in, okay? If I were to graph -1 plus I, what quadrant would that be in? Quadrant 2. Okay, so where in quadrant 2 do we have a tangent of -1? Where does that happen? 3 pi over 4. And you can do radians or degrees. It doesn't matter because this isn't your final answer anyway. Okay, so we have R. Check. We have theta. Check. And we have n. N is the power that you're taking the complex number to. It's 8 in this case. To use de Moivre's theorem then, he says to take z to the 8th power, I'm going to need to take r to the 8th power. Well, r is square root 2 to the 8th. Okay? Then cosine of 8 times 3 pi over 4 plus I sine of 8 times 3 pi over 4. Okay, n times our angle. And then this is where you can use a calculator for some of it. We're going to want exact values, so we don't want to type the sine and cosine in, but like rad 2 to the 8th, you can do that. Do you guys know what rad 2 to the 8th would be? What's rad 2 squared?
2.
Okay, do that 2 4 times, right? What do we get? 16. You can type in your calculator if you need to, though. 8 times 3 pi over 4, that's going to be 24 over 4. I actually like the radians because it makes the multiplication easier. You don't have like huge numbers if it's a degree. 24 over 4 reduces to what? 6 pi. Okay, so now we need to evaluate 6 pi. 6 pi is a little big, so what could we do with it? Subtract 2 pi until we get something that's on our unit circle. So if I subtract 2 pi, I get 4 pi. Subtract 2 pi again, I get 2 pi. You can leave it like that, or you could go all the way down to 0. Doesn't matter. I'm going to say just cosine 2 pi. That's the coterminal angle. All right, and now you can just think about unit circle stuff. What is the cosine of 2 pi? It is 1. What is the sine of 2 pi? 0i. So your final answer for this complex number taken to the 8th power is, you can either say 16 plus 0i, or you can just say 16. If you take -1 plus I and you take to the 8th power, if you FOIL it out 8 times, you're just going to get 16. Everything else is going to cancel. Okay? Now let me show you what it looks like if there's a negative power. This is the same complex number, so we're using a lot of the same information. R is rad 2. Theta is 3 pi over 4. The only difference here is n changes to a -12 instead, just different power. So it would look like r to the n, okay, so rad 2 to the -12th, cosine of -12 times 3 pi over 4, plus I sine -12 times 3 pi over 4, if I can squeeze it in there. There we go. rad 2 to the negative 12th is just the reciprocal of rad 2 to the 12th. If you can do rad 2 to the 12th, you can just take the reciprocal because that's what negative exponents do. They move numbers to the denominator. Rad 2 to the 12th is the same as 2 to the 6th power, which is 64. And if you type this in your calculator, you're going to get a decimal, turn it into a fraction. It's going to tell you 1/64. That's what it is. If I do negative 12 times 3 pi over 4, I get negative 36 over 4, which reduces to negative 9 pi plus I sine negative 9 pi. Okay, so that negative 9 pi is too small, so we can just add 2 pi a bunch, right? If I add 2 pi once, I get negative 7. If I add it again, I get negative 5. If I add it again, I get negative 3. If I add it again, I get negative 1. If I add it one more time, I get a 1 pi. I have to add 5 sets of it on there. Okay, so cosine pi is a coterminal angle plus I sine pi. All right, what is the cosine of pi? Negative 1. What is the sine of pi? 0i. And this one ends up being negative 1/64. It does not always have a 0i when you do this. This is just like happy coincidence for this particular type of problem. Often you will also have an I term. It just happened to be 0 for this one. Okay. Any questions using de Moivre's theorem? I just got one more example, then we're done. Okay. All right. So de Moivre's theorem works as long as you have a whole number power. There is a different version of the formula that allows us to find roots of a complex number, square roots, cube roots, fourth roots, so on and so forth. Write this down. Pretty much everything is the same here. You have an r, we know how to find that. We have theta, we know how to find that. N is the root that you're taking. So if it's a square root, it's a 2, or if it's a cube root, it's a 3. So we're going to be given that. The new guy that shows up here is k. K will have different values depending on what root you're finding. K is all the numbers from 0 up to 1 less than your n value. So for example, if my n was 3, if I were taking a cube root, my k's would be 0, 1, and 2. Okay, or if I were taking a fifth root, my k's would be 0, 1, 2, 3, 4. I would have 5 of them. Why do we have 5 different k's? Because if I take a fifth root, there's 5 answers. Or if I take a cube root, there's 3 answers. So we actually use this formula that many times to get all of the roots we're looking for. Again, it looks a whole lot more complicated than it actually is, I promise. This formula right now, bless you, is written with degrees, 360 degrees. If you want to do the problem with radians, you just put a 2 pi there instead. Okay. All right, so our last example. We are going to find the 3 cube roots of negative 1 plus I, and we are going to leave our answer in polar form. It wants the argument in degrees. We're going to use degrees. Okay. Negative 1 plus I, that complex number is the one we just used in the last problem. Okay. If you didn't have it already, you'd have to find r and theta, but we just found it. We knew r was rad 2. And we knew theta was 3 pi over 4 in radians. We want degrees, so we're going to use 135 degrees. Okay. Because it says cube roots, n is 3. And because it's cube roots, I need 3 values of k to get my 3 answers. And you always start with 0. 0, 1, and 2. It should be 0 up until 1 less than whatever your n is. When you set up this formula, you're going to do it 3 times. And we're going to do all 3 of these, but I'm going to show you a shortcut afterwards so you don't actually have to like use the formula 6 times if it's a 6 root. There's a little bit of a shortcut. Okay, so use it 3 times, and each time the k value changes. Our k's are 0, 1, and 2. Plugging it in. For the first one, r is square root 2 to the 1 over n power, so to the 1/3 power. Cosine, my angle 135 plus 360 times 0, where n is 3, plus I sine, fill it in, 135 times 360 plus 360 times 0 over 3. Okay. And then we simplify that. Now, a square root you can think of as this is 2 to the 1/2 to the 1/3. Okay? To simplify that, I'm not going to get a nice pretty number. I'm going to get a decimal if I put that in my calculator. But you can just use an exponent property that says power to a power. If they're separated by a parentheses, all you have to do is multiply those exponents together. So I can at least say it's 2 to the 1/6 power. It's going to be out front. And that's as far as I can go with an exact answer. Okay, then you just need to simplify what you see for that angle. 360 times 0, that's easy. It's 0. Plus 135, so my numerator is 135. Divided by 3, it's 45 degrees. And you can get the same thing for both of them. And that's your first answer in polar form. Okay, if you wanted to simplify a little bit further, you could, put it in rectangular form by evaluating that. But that's it. Okay, now the only thing that's going to change for the remaining problems is the angle, right? K doesn't show up here. K shows up right there. So that's the only thing that's going to change from one answer to the next. So for the rest of them, you're going to have 2 to the 1/6 out front. And you just have to figure out, if I change that 0 to a 1, what does my angle look like? Okay, well, 360 times 1 would be 360. Plus 135 would be 495 divided by 3. What's 495 divided by 3? I think it's 165. Is that right? Okay. That's it. There's your second answer. And let's do the last one. If K is 2, it's going to be 2 to the 1/6, or the 6th root of 2. And then I'm going to make K is 2. So 360 times 2, 720. Plus 135 is 855. Divided by 3, I think that's 285. Am I right?
Yeah.
Yes. Okay, now here's a little trick that can actually save you time once you get that first answer. Come on, computer, don't die on me. That's the last thing I have to say. All right. Look at the angles. 45, 165, 285. What are they going up by? They're going up by 120. 120 happens to be 360 divided by 3. Why would I divide by 3? Because that's the end. That's what you're going to increase by every time. In general, it's going to go up from one angle to the next by 360 over n. So let's pretend I was finding the 4th roots. 360 divided by 4 would be 90. So once I find the first angle, you can just add 90 to get the other 3. That's the only thing that's going to change. That's a quick little shortcut. Okay? And that is all of 7-7. Whew! We did it. All right, next week, a little more low-key, all right? So we've got Math Excel Workday, last quiz. We've got 2 small lessons. Our very last lesson, Wednesday, Thursday, we've got delayed starts again. It's over parametrics. It's an extra section similar to this kind of stuff. And then after that, it's just final exam review for 6 days. The exam review is already posted for you if you want to start checking things out. And then next week, I'll get you hard copies of things if you want to see details of how grades are calculated. All that's in Polaris for you in the next couple weeks. You can always look ahead if you want to. Okay? Any questions for me? No. Perfect. All right, I'll do cell phone lotto. And I think I have something to pass back to you, too. So I'll get those. Maybe. 8. What do I have to pass back to you? I have quizzes to pass back to you. Over vectors, your favorite. Your groups. Your groups. And yours. Okay, so again, we'll see some of this pop up again on the exam. If you have questions about something, let me know.